Hello everyone, I'm Sabir. Today I'll be discussing my project, which is Emotify. It is basically related to a human facial expression detection using contactless, methods. So imagine a world where Wi-Fi signals don't just connect us to the internet; they can also read our emotions. I'm basically talking about human emotions. So I know it sounds futuristic, but today I'll take you through our journey of making this idea a reality. But before we begin, let's ponder that how many of us believe it's possible to detect human emotions without cameras, wearables, or even speaking, like just through Wi-Fi signals, like detecting human emotions. It is awesome, I know. So it may sound impossible, but I'm here to prove not only is it possible, it's already working. Okay, so before we jump into emotion classification from using Wi-Fi CSI spectrograms, which is very cool, let's start with the backbone of our system, which is basically channel state information or CSI. So what is CSI? The science behind it. So every time we breathe, move, or even blink, we disturb the Wi-Fi signals around us. Like even when I'm talking right now, so I'm disturbing the Wi-Fi signals because Wi-Fi signals are all around us now in this age of technology. So CSI is basically what captures the subtle variation in signal strength and phase. So we will talk about signal strength and phase, and we will also look at its mathematics. So we used a low-cost microcontroller like ESP32 to passively record these signal changes. No cameras, no variables, and no active participation required. So let's look at this slide for a moment and let's try to visualize what I've done. So, yeah, so it is the same thing. Our mission was to, devise a system which is non-intrusive and which is intelligent like framework which exploits Wi-Fi infrastructure to identify human emotional states without cameras or wearables. The privacy violations, you know that it is a problem, and even lights like dim light is, not uh, workable with cameras. And when you talk about lights or when you talk about walls, behind walls also like cameras and wearables, they fail. But wearables are also, they cause discomfort. So these are the factors which led to this system. And this system is like intelligent, this system is low cost, and environmental friendly. So yeah, we'll talk about the experimental setup as well, that how is it working. So Emotify framework, CSI sensing, real-time edge interference, these are like some of the benefits. The proposed system is that the ESPs will be working like the transmitter and receiver. Receiver will receive the CSI packets and it will process the CSI. And after processing, it will apply feature engineering. And after feature engineering, we will have the 2D images in spectrogram forms, which are like what? The spectrogram images are useful, they carry useful information, and using those we will train our model CNN. So processing raw face or raw 1D to 2D, the pipeline is like this, like yeah, the 64 subcarriers, they carry unique information. Each subcarrier is unique, and we are talking about 64 subcarrier edge of ESP32, which is like we can talk about others as well, which is RSS as well. Like, they are not as low cost and like effective as ESP32 is. Yeah, so clean spectrograms then. The experimental setup is just that person is sitting between the two, like, hardware microcontrollers. We will look at a demo as well for more clarity. And we talk about line of sight here, that the person should sit between the line of sight so that, the human subject is seated directly along the line of sight between the transmitting rod and the receiving antenna. So yeah, there are like limitations to this method as well, that the range, and the line of sight, and we are in a controlled environment in a conference room to reduce noise. And yeah, there are like limitations with it as well. But we will talk about how much effective it is and how we can improvise, this. So yeah, the hardware stack is clear: ESP32 microcontrollers, you know, and then we also will talk about the board rate, that how I set up the board rate, which was like 19500, I guess, to establish communication between the transmitter and receiver, and how I set it up at Arduino IDE, programmed it, and then I programmed it with my Android app, which is right now using Edge AI, which is also like using that trained model. I've trained the model. We'll talk about how I did it shortly, and then we will go into the demo so that it doesn't go very long. Signal configuration, Android host processing, these are the parts. This is the mathematical modeling of CSI amplitude extraction. After getting the raw CSI, what it does is that the hardware, the Android app, it extracts the CSI amplitude so that the noise is reduced. There is so that the bias is further, reduced. With high bias, we know that we have more noise. With variance, sorry, the variance is reduced, and with low variance, then we can say that there is low noise, and then like with low bias as well, there's a trade-off. We'll talk about it as well. So let's come just straight to the pipeline. CSI capture, normalization. Log normalization is basically amplitude extraction. Min max, like augmentation, increasing the data set. Now, we'll talk about this in our journey, that how we used every normalization method, splitting, and how we like came to uh, with an efficient, like model in ResNet-18, and which is now working in EfficientNet, yeah, which is now 90%, giving us 90% testing accuracy, which is like high number. Where we started from 49%. We will go to that journey now. Yeah, image encoding from 1D to 2D, and the edge interference. This is an Emotify spectrogram. It is basically showing us an activity like surprised. Yeah, so sample spectrogram. So the clearer, sharper activity patterns you can see. It came from what? Reflectors and spectrograms. We'll see that how it was without reflectors and how it is now with reflectors. How I applied computer vision techniques to achieve it. So yeah, this is the difference, that with without reflectors there is a lot of disturbance, as we can see in this picture. Like you can see a person is sitting, and now the receiver and transmitter, the transmitter is transmitting, like CSI packets, and receiver is receiving, but it is not as focused as it is with reflectors. So that's the difference, that we achieved a 56% increase in SNR with reflectors. So yeah, this is a comparison. Without reflectors, you can see that it is plain. There is no activity as much clearer as it is with reflectors, and you can see that there are darkish, like frequency bursts. Those are basically showing us the subcarriers, the frequencies, and the change in like the temporal features, how we are extracting features. Yeah, this is the data set which I worked with. I had like 60, 60, 60, 60, 60, like 600 without reflectors, 940 with reflectors, so 1500 total around data set. Okay, so I know it is a small number, but it is what we collected. We collected our data set ourselves, and we experimented it with it, and now we can even increase it with transfer learning. With transfer learning, what we have is that we know that ImageNet has 1.2 million images. So if we use ImageNet, we'll have extra more data set, huge data set, and it has already learned, like edges and shapes. So it will help us with images, because with facial expression and with images, we know that these are important, that edges, to identify the edges, to identify the shapes, to identify the segmentation of an image. So yeah, it will help us. So yeah, this is our model evolution journey. So I will go straight to the demo now. Here, you know, like yeah, like what was our environment setup first. So this is our environment setup. The reflectors are like between person is sitting behind between the reflectors, and you can see clearer that what it is happening, that the CSI packets are now moving. They are giving expression. A person gave expression, and now on the computer screen we will see that the image is generated, you know, and after generating the image, we'll also look at the result, subcarriers, and you know everything, the code which I executed. So yeah, we see a short demo like how it was working, the environmental setup, and this is the real-time detection in app. This one, I'll showing you a demo that this is a UI of the app, and when we click on like view live spectrograms, we see the blue lines, and like this is basically live CSI packets being received from the receiver, from the transmitter receiver in Android app, and now this is a live, yeah. So the activity is being you know like captured live. So when we will like when a person does movements, subtle like movements, so these like it is being captured by the receiver, yeah. And for every gesture it is like different, it gives a different line. So it is detecting sad now with 5 seconds. Predicted sad. The confidence is here like 314, which is bug. We fixed it, and we like after fixing it, then we were had it like out of 100. Confidence shows how much it is like being accurate number, how much it is an accurate number. So yeah, like this was emotional test, and this was live view of spectrograms demo of the app. Yeah. So I hope that the demo is clear. So yes, let's come like to our journey of how we trained our model. So for training purpose, I have like research paper of or FIP as well. Like we worked on it. Uh, like Career Expo, we represented our project uh, at a high scale demo expo at Comsat University, where we received this certificate, signed by our HOD respective. So it is just a credential. So now coming to like what we did in model training, this was our pipeline: emotion classification, Wi-Fi, CSS spectrogram, model development, experimental analysis. So our true target was to acquire generalization, means that how much it is generalizing well on unseen data. Because on training data, it was generalizing well. But when we talk about testing accuracy, our training accuracy was high initially. Testing accuracy was low, means that it was overfitting. So what we did is that we came up with like method like we use CNNs, like as I've discussed it already, with like 80% training, 10% validation, 10% testing, which is a like common practice, but 80% CSV, in training. In training we had 80% data. So experiment one, ResNet-18, in our program spectrogram images in RGB. Okay, so we choose ResNet-18 as it is simple, fast, deep learning model for image classification. Uses skip connections which help it learn better, even when if the model is deep. So yeah, we started with it. What we had is that we had low bias initially, but we had high variance. High variance because it has a lot of noise, and there was a problem with the model architecture. So that's why what happened is that our model overfitted. Okay, so we learned from this experiment that yeah, we should not use like yeah, we should not use raw like CSI spectrogram images. We have to do something. We have to filter it. We have to augment it. Okay, so for experiment two, what we did is that there was a lot of data leakage. Yeah, so now these spectrograms. So for experiment two, what we did is that we used efficient net because it is deeper than ResNet-18, and because like what we wanted is that we wanted to reduce our like variance. But what happened is that we applied slicing and augmentation, and the variance increased even further, and the testing accuracy, it decreased even further. It was 49% to experiment one, and it came to 39%, again 34%. It happened because of slicing, we cutted the temporal features, and what happened is that even extra noise was added. So we learned that, yeah, like with better architecture, we also need a better pre-processing method. We cannot direct split it like this from overfitting to generalization. Overfits and fails on new data, balances width, depth, and resolution. So we see that the gap is increased even further here, like test accuracy 34%, and the training was, I think, yeah, there was a gap here. Here, you can see, the green line is basically training accuracy, and the yellowish line is test accuracy. So it was increasing, the gap was increasing here, as I know. Yeah, here we can see that the training is, like it was increasing. We have to reduce the loss. So yeah, this was what happened. So then in experiment 3, we used absolute difference method. With absolute difference, what happened is that we further removed the noise. And what happened is that we also did slicing, so random split led to possible data leakage, but are kept in the same split, ensuring fair evaluation on unseen individuals. So with this experiment, what happened is that better separation of emotional signals improved validation and test accuracy, and model learned meaningful patterns more easily. So yeah, so with augmentation, we see that it was now 44%, like test accuracy has increased, you know, and without it was 42%. So it is better than the experiment 2, which was 34% test accuracy. So yeah, with absolute difference, method, we see that the noise is removed. Now we have a better pre-processing, like architecture, model architecture. So yeah, the gap is now further reduced, which was increased in the previous method. In the previous method, we did slicing straight away and we applied augmentation. But here, what we did is that better. So we can see the comparison that raw RGB, here we had RGB in experiment 2, and in 3 we have absolute difference with slicing. So with improved data splitting is important, because if you have a person's data in both training and in both testing, you know CSV file, what happened is that it memorizes it, then it cannot generalize well. So what we did in person wise data splitting is that we try to keep one sample of a person in one, like CSV file, so that it generalizes well on unseen data. And like this, what we did is that we increased our models, like testing and training accuracy. Okay. So yeah, with these methods, we achieved 47% test accuracy, which is not a high number, but it is a balanced number, because that we focused on true generalization, eliminated data leakage, okay, more reliable. Okay. So yeah, overfitting matter resolved, and I learned a lot, like about like how to apply normalization techniques, secularization techniques here in these methods. And yeah, one more question, that why we did not use ANN, why we did not use RNN, because they are not good for like image classification like CNN, and they cannot learn well from temporal features, and they are like built for like more, I would say that they cannot learn a lot of long contexts regarding image. So it's getting longer, I'm sorry. So yeah, if we, then we improve model performance with reflector spectrograms. Okay, with reflectors, we can see the enhanced signal reflections. Um, and then like we also tracked our mistakes using like confidence matrix, confusion matrix. Okay, so after backtracking with confusion matrix, it increased a lot, things improved. So yeah, coming straight to that, what we did is that then we used mobile app, okay, in Android, which we what we do is that we connect ESP to that phone via USB, stream CSI data, then it computes amplitude, which we have seen already, mathematical formula for each subcarrier, and then displays light spectral, runs dot script model for real-time motion prediction. Pipeline ESP32 to USB to amplitude to spectrogram to emotion. So yeah, I'm coming now straight to my slides that as I showed like we have talked about the real-time detection. I showed you the demo as well. So yeah, so with this I would say that I'll finally show you my research paper, that this is our research paper which we have like worked on and we are still working on it. We have a lot of mathematics here regarding our project. Yeah. So I would really want uh, help in this regard, that working on it and making it, converting it into a real product is what I aim for. And right now I have like the hardware and I have the resources, but I'm lacking funds and I'm lacking like uh, the final touch. From final touch means that there is to work needed to be done. Like I am thinking of adding more components, of like improving my data set, maybe like for real time emotion detection, as I know that there are a lot of like available products in the industry. So studying brain and studying like neurology, I think it would help me that how human brain works and what are the patterns and how I can, like maximize my product's ability to detect images in real time. So yeah, for that it is a future work, I know. But right now, this app, like which I'm working on, its application lies in biometric identity. It can work there. It can work in healthcare systems. You know, like here. Here I'll come. Where was it? Yeah, it is here. Yeah, it's here, I think. Yeah. So, yeah, with this, I would like to end my presentation. So, yeah, biometric identity gesture systems, like even a person is sitting like in a room and there are lights and it can detect the person's mood and it can use IoT and it can play a music according to his mood, or it can like they control the lights according to that person's mood. In healthcare, privacy is very like integral, and in places where privacy is to be ensured and where like lights are not as brighter or there's a problem with the other parts of the of that, you know so there it can work effectively. Thank you so much.